Hello everyone, welcome back to Logic Binder. In today's video, we'll learn the construction of DFA. Consider the first example. Design a DFA for a language starting with A with input alphabet as sigma is equal to A, B. Now, let us assume the language as L, which is accepted by the DFA M, such that the language is L of M is equal to set of strings W, which are in the form of AW for all strings belongs to sigma. We have observed the sample strings AAA, ABA, ABB, AAB, AB, which are in the form of AW. Here W is a string of A's and B's. In the next step, we'll construct the minimal automata. The minimal automata is nothing but from the initial state Q0, we need to read the basic string. Here the basic string is the language starting with the character A. So from the initial state Q0, upon reading the input character A, it is reaching the next state Q1. In the next step, we'll give the remaining transitions to the minimal automata. Next, construction of DFA. For the above minimal automata, we have to give the remaining transitions. In the minimal automata, we have seen that from the state Q0, the input symbol A is already processed to the next state Q1. Since it is a deterministic finite automata, we have to make the transitions as Q cross sigma derives Q. It means that for every state on each input symbol A and B, we have to define the transitions to the next state. So Q0 on A is already defined. We have to define the transition of Q0 on input B. Since the language is in the form of AW, the string should not start with B. Upon reading an input symbol B from the initial state Q0, so it is directly connected to the hang state or a dead state, which is taken as Q2. Similarly, we have to give the transitions to the Q1 state and Q2 state. So Q1 upon reading an input symbol either A or B will be remaining in a same state Q1 because the string is having a condition that it should begin with the symbol A. After this A, we can have any number of either A's or B's. So this transition is allowed, which is Q1 upon A or B can remain in the same state. Similarly, Q2, though it is a dead state or a hang state, should be defined with A and B transition. Since it is a DFA, for every state on each input, we have to define a transition. So Q2 upon reading either A or B will be remaining in a same dead state. Thus, in the DFA, we'll be getting total number of transitions as Q cross sigma derives Q, which is 3 states on 2 input, total 6 transitions will observe. Consider the sample strings AA, AB, which are belonging to the language L of M. Here from the initial state Q0, A is reaching to the final state. So this is a valid string. Similarly, AB from initial state Q0, B is also processed through the final state. So these two strings are belonging to the language L of M. Based on the above transition diagram, we'll write the transition table and transition functions. Let us observe the transition functions here. From the diagram, it is given that Q0 upon reading A is reaching the next state Q1. So delta Q0 on A is equal to Q1. Similarly, Q0 on B is moving to trap Q2. So delta Q0 on B is equal to Q2. And Q1 upon reading both A and B is moving to the same state Q1. So delta Q1 on A is equal to Q1. Delta Q1 on B is equal to Q1. And Q2 upon reading A or B is remaining in a same state Q2. So delta Q2 on A is equal to Q2. Delta Q2 on B is equal to Q2. So these are the transition functions occurred in the given DFA. Similarly, let us plot the transition table. In the transition table, we consider rows and columns as set of states and input symbols. So the cell entries will be given from the transition functions or transition diagram. If we observe the transition diagram, in the transition diagram, Q0 upon reading A is moving to the state Q1. So Q naught on A is equal to Q1. Q1 will be the entry at this particular cell. Similarly, Q naught upon reading B is making a transition to the state Q2. So Q naught on reading B is moving to Q2 state here. Similarly, Q1 on reading A is moving to Q1. So Q1 on reading A is moving to Q1. In the same way, Q1 on B is moving to Q1. So Q1 upon reading B is moving to the same state Q1. And Q2 on A is moving to Q2. Similarly, Q2 on B is making a transition to Q2. So this is a corresponding transition table for the given transition diagram. Thus, in the DFA, we'll observe total number of transitions are for every state on each symbol, we'll make a new state transition. So for 3 states on 2 input symbols, we'll have total 6 transition. The resultant DFA is given by the phi tuple, which is Q sigma delta Q naught F. The phi tuple here is set of states Q naught, Q1, Q2, input alphabet A, B, initial state Q naught and the final state F. Next example is design a DFA for a language ending with A for input alphabet A and B. Let us assume L is a language accepted by the DFA M such that L of M is a set of strings W which are in the form of WA for all W belongs to the sigma symbols of A's and B's. Here the sample strings observed are AA, BAA, ABA, BA, BBA. In this language, the language is ending with the symbol A. Based upon this sample strings, now we have to construct the minimal automata. So construction of minimal automata. In the minimal automata, will generate the sample string or a basic string from the initial state to the next state. So Q naught, which is an initial state, upon reading a basic input symbol A, is reaching a next state Q1. In the next step, we'll give the remaining transitions to the minimal automata. After constructing minimal automata, upon giving a remaining transition, in the next step we'll construct the DFA. So in the DFA, we'll consider the minimal automata, which is Q naught upon reading A is reaching the next state Q1. Since it is a DFA, we need to mention on each state for every input symbol we have to derive a next state transition. So Q naught on A is already processed. So we have to define the transition for the state Q naught on input B. So Q naught on B can move to the same state Q naught because the language is a set of strings which is ending with A. In front of this A, we can have any number of B's. Similarly, we need to define a transition for the corresponding state Q1. Q1 upon reading A can remain in the same state. No need to change to the next state because the language is ending with A. So here we can give the transition to the same state on a symbol A. So Q1 on B should go to the next state, which can be the initial state. Instead of taking a new state here, we can give the transition back to the initial state Q naught upon the input symbol B. So Q naught on A is completed, Q naught on B is completed. Q1 on A is completed, Q1 on B is completed. Thus we can say it is a DFA. Since the transition rule Q cross sigma derives Q is satisfied. 2 states on 2 inputs is reaching a next state Q. Thus in this DFA we will be generating total 2 states on 2 input, total 4 transition functions. Consider the sample strings. So the sample strings are the minimal string A and AA. Q naught on A is processed through Q1. Q1 on A is going to Q1, which is the final state. This is also valid. AABA. Q naught on A is going to Q1. Q1 on A is going to Q1. Q1 on B is going to Q naught. Again Q naught on A is moving to the final state Q1. So this is also the valid string which belongs to L of M. Upon construction of DFA, in the next step we'll write the transition table and transition functions. Consider the transition diagram. From the transition diagram, it is observed that Q naught on reading A, it is reaching the next state Q1. So delta Q naught on A is equal to Q1. Similarly, Q naught on B is making a transition to Q naught. So delta Q naught on B is equal to Q naught. And Q1 on A is moving to Q1. Q1 on B is moving to Q naught. So delta Q1 on A is equal to Q1. Delta Q1 on B is equal to Q naught. Next, we'll generate the transition table. In the transition table, we'll consider the rows and columns as alphabet AB and the states Q0, Q1. And this transition table entries are given based upon the transition diagram or transition function. Let us observe the transition functions. Here delta Q0 on A is equal to Q1. So Q0 on A is entered as Q1. Similarly, Q0 on B is entered as Q0. And delta Q1 on A is equal to Q1. So Q1 on A is taken as Q1. Delta Q1 on B is equal to Q0. So Q1 on B is taken as Q0. Thus, the resultant DFA is given as phi tuple Q sigma delta Q0 F, which is Q is the Q0 Q1, sigma is AB, initial state Q0 and final state Q1. In the next example, we'll design the DFA having A as a substring with the language of symbols A and B. Let the language L of M is a set of strings which are in the form of WAW. Here A is a symbol which can be substring, so it can be in any position. W is a combination of the symbol A and B. Here the W is a combination of a symbol A and B. Thus the string can be in the form of the substring A with either prefix as a W and suffix as a W for all the strings belonging to the sigma A and B. So the language will have the sample strings A, AB. Here A is a prefix. B, AB. Here A is at the middle. B, AA. Here A can be at the suffix. A, B, A, B, A. Here we consider the symbol A at multiple positions. Based upon the sample strings, now let's construct the minimal automata. The minimal automata is nothing but processing the basic string. The basic string is a substring which is having the symbol A. So from the initial state Q0, upon reading A, it is reaching the next state Q1. Based upon the minimal automata, we'll construct the DFA by giving a remaining transitions. Based upon the minimal automata, in this step we'll construct the DFA. In the construction of DFA, we are giving the remaining transitions for the states. So here from the state Q0, A is already processed to Q1. The remaining transition for Q0 is B. Since the language is a set of strings having A as a substring, in front of this we can have any number of A's or B's. A transition is already done in this DFA, so we are left over only with the B transition. So Q0 on B can remain in the same state Q0. Similarly, we have to give the transitions for Q1. Since the language is having A as a substring, Q1 on reading A or B can remain in the same state Q1 because the sample string can be B, A or B, A, B. So the A is processed as a substring here. So this is a valid transition where Q1 on A or B can remain in the same state. Thus in this DFA, we are getting total Q cross sigma derives Q number of transitions. That is, for 2 states on 2 input symbol, total 4 transition will observe. Let us observe the sample strings. Q0 on reading A is moving to Q1. Q0 on A is moving to Q1. Q1 on B is moving to the final state Q1. Q1 on B is moving to the final state Q1. Here we have A as a substring. Q0 on A is moving to Q1. Q1 on A is moving to Q1. Q0 on A, Q1 on A is reaching a final state. So this is also valid string. Q0 on B is moving to Q0. Q0 on B is moving to Q0. Q0 on A is moving to final state Q1. Q0 on A is moving to Q1. So this is also belonging to language L of M. After construction of a DFA, from the transition diagram, we can plot the transition table and transition functions. Let us plot the transition table. Q0 on A is moving to Q1. So Q0 on reading A is entered as Q1. Q0 on B is moving to Q0. So Q0 on B is entered as Q0. And Q1 on A and B is remaining in the same state Q1. So Q1 on A is Q1, Q1 on B is entered as Q1. Similarly, we can generate the transition functions. Q0 on A is moving to Q1. So delta Q0 on A is equal to Q1. Q0 on B is going to Q0. So delta Q0 on B is equal to Q0. Q1 on both A and B is remaining in the same state Q1. So delta Q1 on A is equal to Q1. Delta Q1 on B is equal to Q1. So in this DFA, total will generate Q cross sigma derives Q. For 2 states on 2 input, total 4 transitions we are defining. Thus, the resultant DFA can be Q sigma delta Q0 F, which is set of states as Q0 Q1, input alphabet AB, initial state Q0, final state Q1.